So guys, I got quite a bit of feedback. People are saying we should cover some of the GNNs in this course. So to do that, what we will do is we'll have to be a little bit brief and move a bit faster.
Sure.
I'm thinking that we have done a lot of fine-tuning. We could make today the last day of fine-tuning. So if we follow that, is there any protest to that? How many of you would like to have one more day of further fine-tuning?
What would we cover in that further day?
Basically, in fine-tuning, this is more of a vision or an image and data fine-tuning.
Right.
We would like to see an example of enterprise data where textual fine-tuning.
We're coming to that. Coming to that. So guys, yeah. So I must make initially you were saying something.
So yeah, if we did another day of fine tuning, like what would we do in that day?
That's what I'll show right now. And then let's decide whether we want another day or some things we leave as self-learning.
We have key of the room. I locked. Thank you.
Bring it back. Yeah. So guys, let's recap what we did. We have been doing fine-tuning with just PyTorch. We have been doing fine-tuning with Hugging Faces. We took an interesting example of with Hugging Face, we did fine-tuning with Lamini. Now we did Lava fine-tuning. By the way, how many of you tried the code? How to custom fine-tune? Did it work? Prakash, did it work?
No, we tried like we were a very early stage.
You haven't
we
finished.
We went to their website.
Yeah.
Lava, and it was failing.
Actually, there was some mismatch in there are two versions of the code available. Deep learning, you're talking deep learning.
Yeah.
So one is the latest one, it was not working, but I went back to the previous one, it was working.
Oh, is it?
Yeah.
You mean the Lava model?
The one in deep learning, I think it is a deep learning.ai course.
Oh, no. I'm talking about Lava.
Oh.
Lava. How many of you tried the Lava custom fine-tuning Lava? I would strongly suggest you do that, guys. And so what we are going to do, so having done this, what are the things that we are going to do? What we are going to do is, and I can just sort of talk through it and give an idea. We are going to learn about very easy frameworks to fine-tune. Two recent frameworks that are gaining quite a bit of traction are one called Unsloth and the other called Llama Factory. Today I'm going to give you a quick walkthrough. I was going to do a much faster walkthrough, but in hindsight, I feel that now you know enough. And these are very easy frameworks, some of which you can do on your own. I was going to talk about one particular fine-tuning technique that does merit a lot of attention. It is the PEFT, parameter efficient fine-tuning. And in the parameter efficient fine-tuning, there are many methods. There is, for example, soft prompt or prompt-based fine-tuning. Then there is like ways to do fine-tuning by changing the way you deal with attention itself. And then the most popular, I suppose, is the LoRa way. And LoRa is something, if you remember, we covered in Bootcamp 1. So what I have done, and I've also covered it in the Wednesday paper readings once. So I have posted the video from LoRa, from your Bootcamp 1. The LoRa is low rank adaptation. So today I'm going to just summarize the big ideas from that. So we'll do that. And then what we will do is yet another thing, some new things have emerged. One of the big problems people are asking is, can we do a complete pre-training of a model? To pre-train, I said, takes expensive hardware, lots of time, lots of data. So suppose you have enough data, can you actually pre-train a model from scratch? And so there's been a recent breakthrough that is getting quite a bit of attention is called the Galore. What Galore does is it carries the idea somewhat similar to LoRa, except that it doesn't use LoRa. It uses a full model, but it sort of uses certain layers of the model. And instead of tuning on the parameters, it actually fine tunes on the gradients. It sort of does a matrix factorization of the gradients instead, right? And LoRa, if you remember, is a matrix factorization of the parameters itself, fine tuning parameters, low rank representation of that. So Galore is important. The last topic in fine tuning that I wanted to cover is the fact that you don't need reinforcement learning. The new thing that has emerged is a direct preference optimization. So these were all the topics, and the whole question is, we could, like, in a way, see, I have covered these topics either in the previous bootcamp or in my Wednesday paper readings. If you're willing to take these as reading assignments on your own and watch these videos, we can save ourselves a day and squeeze in more interesting things. Like, for example, graph neural networks will be back in.
Let's do that, As.
Let's do that. Okay. So one thing that I would say, when you see this direct preference, this quiz, associated with it, I will add it here. The quizzes are making their way back in now, but if you want to get a taste of that, you go to weekly paper readings and you go to direct preference optimizations here. All of you have access to it. You'll see that the quiz and the question answers are there, right? I'll copy it over to this course itself.
So I don't see the quiz here in the portal yet.
Yeah.
Oh,
In this portal, I still have to copy it over, but you can, if you are in a hurry, go and take it there. So just to summarize, our afternoon is there. I want to introduce you to some libraries that have recently emerged, and this continues the curve of making it easier and easier and easier to fine tune. I suppose the ultimate goal will be you lie down in bed and say, fine tune my model in this data, and it will get fine tuned or something like that. And we seem to be reaching that level of simplicity when it comes to fine tuning models. Right? It's literally coming close to that. I don't know how much more easier we can make it. So I'm hoping that I'll just spend no more than 20 minutes on this, right? And we can move forward with that. So before I do that, let me show you a data set that we can use as a baseline for fine tuning. There is why is this? Actually, let me turn off the light. Albert, could you mind turning off the light? I'm getting a lot of glare. Oh yeah, here it is. When you look at this data set is made up of tiny stories. As they say, one day a fast driver named Tim went for a ride in his loud car. He left to speed down the street and feel the wind in his hair. As he drove, he saw a friend Sam standing by the road. Hi, Sam, Tim called out. Do you want to go for a ride? Yes, please, Sam said. They drove off, blah, blah, blah. The car had a great time together. As you can imagine, this is a tiny, literally as the data set says, it's a tiny story. A lot of them start with once upon a time, right? So this is a data set that we'll use to tune some models. What do we want to do? Suppose you want to take a model. Let's take a tiny model. Usually, if you want to fine tune and you have your hardware, I would strongly encourage you to take small models, very small models. Right? So these days, in the world of small models, I would strongly encourage, like, for example, Gamma 7B is very small, or Mistral 7B is very small. Take models of this size, or even smaller. So I will take one of these to illustrate the point. So what are we trying to do? We're trying to teach an LLM, a general purpose LLM like Llama 2, Mistral, Gamma, etc. We are trying to teach them for one task. Remember, fine tuning is task specific, right? Or domain adaptation. Here it is task specific. What is the task that we'll train it on? To write stories, little stories. So let's go and try. Which one should I pick? Let's try Gamma. I haven't tried Gamma.
So can I ask one question?
Oh, yeah, sure, please do.
So there's a bunch of techniques like distillation, quantization, instruct GPT kind of fine tuning, all help in reducing the number of parameters to say 100x. I saw instruct GPT is 100x lower. So everything helps in efficiency. So is there a particular order? I mean, like, can you give a brief? Uh, like how would we go about doing it? Distillation, quantization, the sequence.
That's a good thing. Here is how I would answer it. See, they use different. Yeah, your overall goal is to somehow fit bigger models into smaller spaces. Right. So distillation takes the approach of student teacher. It says, I'll literally make a small model from scratch, right? Which will learn from the teacher. Then that is distillation. But you don't do quantization of the parameters. The other approach, an independent orthogonal approach, is to say, we are going to keep the big model, but we are just going to quantize it. Means from 16-bit, we'll go down to 8-bit. From 8-bit, maybe 4 bits. And now we are trying to go down to 1.58 bits, right? Or 1 bit kind of thinking. By the way, that's a paper reading I'll do soon of bringing, like, what are the trade-offs involved when you quantize a parameter down to just 3 states, -1, 1, or negative, positive, 0, right? So either a parameter is now done, is it negative, is it positive? And it turns out that each of these you sacrifice. The question is, how much do you sacrifice? At this particular moment, Jay, there are no winners. The only winner is go get yourself a bigger hardware, and if you want the full accuracy, use the full model. So for example, when you go from 70 billion to 7 billion, frankly, the loss is so huge that 50% of the use cases go out of the window. When you take quantized 7 billion, which is what you'll have to take, see, here is how it works. If you are going to train a model, for inference, 7 billion is good. You can put it in your GPU and do that, right? But the moment you start training the model, fine-tuning the entire model, you have to talk of gradients. Yeah. This is a point actually not many people realize. I'll talk about that. How should I do that? Paper reading LLM 2. Yeah, let me talk about that. See, what happens is you have what just happened? Forward journey. Let me do this here. I'm situating myself a little bit. Yeah. See, you have a transformer model, right? It has parameters W. Let us say that it has M parameters, right? M parameters. So when you do the forward journey, suppose you give N and you produce Y hat, right, is equal to this entire network X given the weights. This is your prediction, isn't it? Now, there are M parameters involved. So you need storage capacity, roughly speaking, for M parameters, and for matrix multiplication a little bit more. So it will be in the order of M with some extra space for multiplication. But when you fine tune, what happens is that, let's say that you use these days Adam W. You use the optimizer Adam W, right? If you look at the equation of Adam W, it needs the gradient of the loss with respect to the weight. Are we together?
Mm-hmm.
There is a G, let me just say G term, gradient term. There is also a G square term. Now, the gradient has to be computed for every parameter. And this also has to be computed for every parameter. Are we together? So now how much storage do we need? The initial forward journey, forward, gradient, square. This needs M. This also needs M, isn't it? Because you're computing the loss derivative with respect to every parameter, and this also needs M. So how many parameters do you need to store in memory? Like how many values you need to store in memory? 3M, isn't it? So let's say that you have a 7 billion parameter model. If you're fine-tuning it, what happens is just to hold parameters, forget about all the extra space that you need. Just to hold parameters, you need 21 billion variables are there. Variables to store. Are we together? Suppose you do FP16, floating point 16. Now what happens? You're using 2 bytes per variable, isn't it? Are we together?
Yep.
And so that means 42, but when you take in the overheads, actually it's more like 47 GB plus overheads. 45 to 47 GB, which means that if you're fine-tuning, the very, very minimum that you will need, even for a tiny model like this, will be something like a A6000, right? Which has 48 GB memory. The GPU memory, 48 GB. Do you see how expensive it gets? Okay. So, but what do you and I hold on to? In our desktops, we have 24 GB, right? That 24 GB is driving your desktop, is loading the model, matrix multiplication, all the multiplication partial, intermediate states, everything is stored here, right? So what happens is that, as you can quickly see, you can't even fine-tune a model of this size. So that brings about the whole problem. Like, how do you fine-tune even a 7 billion parameter model, which has already become a huge compromise over the 70 billion parameter model? Do you see that? Right? And by the time you go to 70B, you realize that you're looking at 480, right? 480 GB GPU memory. Considering that a typical H100 has 80 GB, it means you need 6 of them minimum. 6 of these in a machine. More practically, you need 8 of these. Right? A typical machine which contains 8 of the 40 H100s, guess what's the price of that?
40,000 per machine.
It's about $500,000. Right?
Might as well just start stealing phones and setting up a server farm.
That's right.
That's
right. Yeah.
To call it liberating the past.
So guys, do you see the practical reason why we need to do fine-tuning using efficient means? Right? So, well, in this particular, we'll come to that. Like, how do you do that? But this is still within the means of what is possible. Now, I must tell you one thing, guys, that some of these with quantization is possible. What you do is, if you quantize it to 8 bits, going back to our discussion, when you go from FP16 to 8-bit, what happens now? Your requirement comes down from 45G to 22 GB, right? It just about barely fits into your 4090. Do you see that, right? So you can actually fine tune it on your 4090. If you go down to your 4-bit, at 4-bit, I don't know how much, like in my view, the degradation is significant, right? You go down to 4-bit, then maybe even your 4080 will start doing the job, right? So, I mean, or maybe your Macs will kick in at that moment. That's why 4-bits are so popular on Macs.
So actually, Asif, the degradation is not that bad. So there's an Intel study that they have done across. So they suggest to come to 4-bit, do it on the developer laptops, and once they're happy with it, run it in the actual data center production. So they have accuracies from 4, 8 to 16, and they've run it across quite a few models. And so the
No,
degradation
Sachin,
is like,
I've seen those studies. So thank you for bringing that input. As Sachin points out, there are benchmarks that show that when you go down to 4-bit, you don't lose that much. You lose about 5-10%, right? But from the benchmark perspective, yes, this is true. But from real world perspective, when you're building things, like in my case, right, I'm yet to be able to use any 4-bit quantized model in a real world situation. For projects that I'm doing, I'm not able to use 4-bit. Maybe I'm not doing something right, but I'm simply not able, the results are not satisfactory. They're just not coming out satisfactory to use for the use cases that I have. Yeah. But benchmarks say you lose only 10%. That's true. When you actually see what it is, for example, you'll notice that a 4-bit, ask it to generate a text, ask it to generate a long text, and you will see that it doesn't produce good results at all. Yeah. So unless things have changed and I'm still using some older models, that's my experience at this moment. Of course, now there's a paper you can go down to 1.5 bits.
And what about for like edge computing cases? Like, so you want to run like some of these bigger models like on your phone, like you have it as part of like an app or something. Would that be like a valid use case for using something like 4-bit or below? Because you need to have it relatively small for it to run on the.
See, what people have actually, yeah. By the way, I take that back. Sachin, what you are saying is that a pre-trained, once you have trained a model and you bring it down to 4 bits, then the performance looks reasonable. If you try to fine-tune a 4-bit model, it gets into trouble. From my experience. Huh?
yeah, I think that's right.
So Ishila, to your point, if you quantize down to 4-bit and even down to 1.5 bits and so on and so forth, it turns out that for many use cases, not all, many use cases, the forward inference is fine. You train and then you quantize, and then it will run reasonably well. So I'll give you an example. If you're doing basic text classification or any of the classic NLP tasks, NER or things like that, it works just well. But the moment you go into long generative things like reasoning, by the way, reasoning capabilities and so forth, I find that the degradation is significant.
With the reasoning tasks, would it also kind of depend on like how far you've broken down like the tasks, like from a
chain of thought kind of thing? It is definitely true. What I found is that the smaller, tiny models, they have very poor chain of thought capabilities. They just don't do well. In fact, personally, I feel that beyond 7 billion, but even 7 billion is borderline. Whenever I do a tree of thought, I invariably go with 70B or more. Right? It's just experience actually that at 70B or more, chain of thought works very well. So I would consider this whole chain of thought, tree of thought reasoning kind of a thinking more as an emergent phenomenon that doesn't scale down well at all. Yeah, that's my experience.
Are there any?
One second, with Ishile. Go ahead.
But from like an engineering perspective, so you have like to run it on the bigger models is like inherently more expensive. So if you had the ability to use multiple models like in tandem, you would maybe have like the bigger model like break it down into subtasks and then run the subtasks on the smaller models, right? Like, would that be like a valid approach?
It would certainly be a valid approach. I'm trying to remember if there are studies that have looked into it. There must be. I can't recall at this moment. But it is certainly a valid approach. Look into it, see what people have done. Yeah, somebody was asking a question on Zoom.
Yeah, Asif, one question. Are there any standard benchmarks, uh, that people use for every time, they're fine-tuning the model or quantizing the model? Are there any standard benchmarks, or is it,
Oh, there are many
build
benchmarks for everything. Blue, there's that. The benchmarks are the galore of benchmarks. The problem is, and this is one of the realizations people are coming to, two problems we have with benchmarks. Benchmarks, it turns out, are not very reflective of real world situation. A lot of models that shine in benchmark don't do so well in real life. For example, if you go back and look at some of the models that got released and later on people walked away from it, Alpaca is an example from Stanford. When they released it, they thought it's doing very well on the benchmark. When people downloaded it, they just went like yuck, right? So and then they took it off. Stanford got pulled it off. So that's one problem with benchmark. The other problem that we are finding with benchmark is behind benchmark are the data sets. I suppose one of the realizations that people have had in 2023 is most of the publicly available data sets, they have close to 30-40% error rate. That's a very high number. Like when you're competing on 1 or 2 decimal points, like you're saying my algorithm, my model is better than yours because I beat you by 1%. Right? So, for example, if you look at the comparison of, I'm reminded, just not to pick on anyone, but Gemini's paper with comparing itself to GPT and other things, they often say that on this task we are 1%, 2% better. All of those things are predicated on the fact that the benchmarks are good. Behind the benchmarks are the data. Now we know that the data has such a huge error bar that any such comparison is meaningless. Right? So we'll never be able to tell. For all we know, Gemini is far better than GPT or the other way around. But we'll never be able to tell looking at the benchmarks. And that's the problem we are facing.
But that's even true for some proprietary data. Like I
True,
was working with like museum data, and I like for some of like the labels that I was dealing with, like I knew that they were wrong. Like they're just straight up incorrect. Like I had sources to prove that I was incorrect, and I had to have like the museum change the labels. But in that sense, like you kind of expect to have a professor that's like labeling things correctly, like when they publish it in their book or whatever. But like that's just kind of inevitable, right? Like it's very difficult to.
Yeah. You know, somebody, I think wrote a book or something. He called human beings the bozo sapiens. So we are all bozos, right? We make like we go 2 steps in the right direction and 1 step sideways. That's how we do. Even the best of professors. Yeah.
So one question on this 70 billion calculation to 480 GB the GPU RAM. Does model horizontally stay on multiple machines, or
you can do that? That's compute partitioning and data partitioning. That itself is a deep topic, right? And it goes into, now we are getting into the innards of what happens inside GPUs and how these transformers can be partitioned, sharded. Very, very interesting topic. And it gets into the whole compiler topic. Like, how do you compile this? You know, you think you're writing Python code, but that's not how it is done. It has to be translated into the CUDA layers, to the CUDA and so forth, has to be transpiled into the GPU instruction set. And that whole technology is it's a complete field of its own.
And a lot of the papers do actually go through proofs saying that like if we batch it in this way, even if we run it like in parallel to each other, we can still like stitch together the gradients to the very end of like the batch that they run through like the different things. So
that weights and biases are at the batch level and at the top model level.
So,
are
like
they same?
At the batch level, it's different, but then they have like an algorithm at the very end of the batch to basically stitch it back together again and then go forward again. And so they use like a bunch of like, they actually go through like really deep what is it called, like linear algebraic proofs that it has like the same output as if you were doing it.
Yeah, it's a whole world, Prakash. This if you want to go down, right?
It is, maybe we need a different course for that.
You do need a different. I mean, I would love that because that's all numerical computing. I will get very excited about it. So the fair warning: don't trigger that.
don't ask you for a good time.
I can go on and on about matrix multiplication and the beauty of that.
Using large language models, then a 4090 is plenty, right?
If you're not using large language models, yes, 4090 is enough. But because of the emergent capabilities, a lot of the power of large language models literally comes with large.
Yes.
Right? Yeah, Jay, you're saying something?
Asif, I might be jumping the gun here, but it's just a question, Asif. I've been with reading the papers, all that. Now, is there a general rule of thumb in your mind, on how to use these techniques, Asif? If you could, I'm just saying, it may not be today, but at some point.
Yeah, I would love to share my experiences one day, what I have found, but I'll summarize it with this. Jay, what I have found is bigger is better. There's no doubt about it. Like the fact that these models get smarter as they grow, no doubt. So here is the learning that I came up with. And this is what you'll find at support vectors. The sweet spot that I felt, see, you can't go and buy A6000s or A100s or H100s. Those are prohibitively expensive. So here is the sweet spot. Get yourself 4 4090s. 4090, 4090, 4090, 4090, right? When you take 4 of these 4090s, they will cost you approximately 2K a piece. Actually, these days, if you buy a good quality one, it is 2.5K a piece. Right? Then what happens is you get 96 GB GPU memory. Generally, I found that this is the sweet spot between having a little 4090 on which almost nothing can be done and having a H100, a bank of H100s. This is the, price performance. If you look at the price performance ratio, this is the sweet spot. To drive this sweet spot, you'll need obviously a motherboard. And so, which is what we put together. You don't need a very fancy motherboard. It turns out that even if you have something, a modest amount, GB RAM, and a simple EPIC processor, right? For example, 9654 EPIC, which has 96 cores. It may even be an overkill actually for this. But one of you can look up the price of EPIC 9654, what it is, and the price of 512. Obviously, these are ECC registered RDIMMs. I would say that if you are serious about it and can afford it, this is your sweet spot. And frankly, it is cheaper than having it in the cloud. But the only thing is to do is make it yourself. Don't go and buy it. If you buy it, the vendors will charge you twice the price of components.
And Asif sir, you are saying that these are on the one single motherboard, all
single motherboard,
4090
single
mounted on the same motherboard.
Yeah. So what you'll have to do is you'll have to take a motherboard that has at least PCI 16 cross 16 minimum. See, nowadays motherboards come with 6-8 slots.
Yeah.
But the thing is, do they all support the full width X16? X16. So if they do, then you attach risers on it. Because there won't be space to put them next to each other, right? So you'll have to put riser cables. These are your riser cables to that, and then go get yourself a 2000 kilowatt power supply. So where do you get this massive power supply? Look into Newegg and look for power supply under mining rigs. As in Bitcoin mining kind of thing, mining rigs. So nowadays they make such big power supplies. See guys, the same machine that you jury rig yourself, if you get it from the vendor, it will literally cost you twice as much. Yeah? And one of you can tell me what the price of 9654 is, EPIC 9654.
It says 1850.
What's that?
I don't know, 1850.
1850? No, it's not possible. If it is that price, I'll buy 10. Right? So that is the other advice I'll give you. The third advice that I'll give is, in terms of quantization, like up to 8 bits is pretty good. Pretty good. 4 bit. So here's the thing. For everything, 4 bit, good for classical, what I would now call classical NLP tasks, like classification, like zero-shot classification, NER, things like that, very basic. All the classic machine learning NLP tasks, Jay, I find that 4 bit is good enough. But the moment you go to high-end things that require more sophistication, then you need more. 11,000, yeah. 11 to 12,000, yeah. So 12K for the processor. And how much is it? 10K for the GPUs. And then another 4-5K for the rest of the motherboard and memory and so on and so forth.
Is it as good as the 4090?
What do you mean by 4090? This is just the CPU.
Oh, this is from AMD.
You need a motherboard CPU, no? You need it. So guys, this is, if you look at the inference server that some of you are playing with, and this is thanks to Sukhpal, who put it together for us. This is literally the configuration of the inference server that we are running.
Thank you.
Yeah.
Sounds interesting.
Yeah, and some of you are silent. Somebody was asking me, like somebody was having a lot of fun on it. And I asked,
so we can train.
Do you still have access to it, or did you lose it? Oh, okay.
So this is the lab setup we have?
This is what we have back there.
And we can train any LLM?
Not any, not even that. Unfortunately, not even that. Yeah. All you can do is, on this 7 billions, you can do very comfortably. You can do Mistrals and so forth. But frankly, even with this machine, you can't go very far.
And on this machine, you don't need sharding of the...
That is automatically done.
Because it is on the same mother.
On the same mother. Yeah. Yes.
Oh, kind of as like another question. So you say that like 4-bit is good for like classical NLP tasks, but when it comes to discriminative tasks, can you go down even further? Like
that is the claim of this paper that I'm seeing. We'll have to see how good there is. See, ultimately, right, papers are papers. Unless you run it yourself and see what happens, it's a little hard to tell.
And also for the use case, right? Like depending on the data and depending on like the conditions, it's going to change. But just from like a perspective of like, if you were really strapped on computational space, you might have like a larger model, like orchestrating like the tasks of a smaller one, but then have like a bunch of teams like doing really specific subtasks that they can fine tune for.
Yeah. So Ishila has asked this question. For I'll just rephrase it for everyone. Let's see, are you better off quantizing a larger model, or are you better off starting with a smaller model itself without quantization? They're two opposites. And if you end up with the same size, generally people believe that quantizing a bigger model is more effective than a full precision smaller model. While that has been the belief, research work like, for example, Microsoft's Phi and Phi 2, which started with a provocative title, "Textbook is all you need." This line of research makes a different claim. It says that small is good enough so long as you train it with really good data, right? And it begins to compete with much bigger models. So it's a pretty unclear situation now. My own bet would be that you're better off quantizing a bigger model because you preserve some of the emergent behavior, emergent abilities, rather than just having a very small model at full precision.
Yeah, okay. So this kind of also ties into some of the other stuff, not to keep on dragging this point out, but to the other stuff that we were talking about with like the parent-child models as well. Where you
distillation.
Where you do distillation with like a larger model.
That's right. It holds true there also, yeah. All right, guys, so that's that. Now, getting back, let's look at this framework called Unslot. So Unslot, I will just walk through the code, guys. Huh? Now, when you do Unslot, if I may recommend, if you have Colab, I'll do it in Colab. For heaven's sake, change the runtime to A100. Right.
So you can only do.
No, you can do it on very small ones, but my experience is that you're far better off changing. See, if you're paying for Colab anyway, what is that?
Yeah.
Like $10 or $50 a month? Why not? So do that, and then you will have to install some specific versions, etc., etc. That is okay. Now let's look at what it is doing. These are the 4-bit quantized models. Right? Now again, it's 4 bits. You can use 4 bits, load in 4 bits too, right? You can set it to false. You can set the full model. And then let's see how it works. What is the code for this Unslot? Fast language model is a class that belongs to Unslot. Do you notice that it looks very much like either PyTorch or like Hugging Face, the API? Right, pre-trained, a model name, sequence length, D-type, that is it. And then what happens is that you get the PFT model. What are PFTs? Right, parameter efficient fine-tuning model. We are going to talk about that. In particular, we are going to talk about the LoRa's and so on and so forth. Right. So you got the model token, and then we now add LoRa adapters. We need to update 1 to 10% of the parameters. What does that mean? So LoRa, guys, do you remember LoRa, us doing LoRa in Bootcamp 1?
Yes.
Do I need to really go into the details, or that is fine? Quick summary should be enough.
Summary should be.
Yeah, quick summary.
Okay, so I'll just give you the foundational concept of LoRa. But it uses LoRa. Just think of it that if you are going to fine-tune a model, your first response should be LoRa. Are we together? LoRa family, not just LoRa. LoRa is a whole family of models. You should go with LoRa. Then, this is just the instruction format. Do you notice, guys, that whenever we think of instruction, the classic pattern is instruction, input, response. Another way to say it is question, input, answer. Right? It's a generalization of question, input, answer. Instruction, input, response. That's your classic instruction template. Are we together, guys? So what are we doing? What is the exercise they are doing? They are going to fine-tune a model for some task. Right? And we are not going to use this for text completions, etc. Nothing magical here. Now you have data, some examples. Where are the examples coming from? Let's go and look, where did they load the examples from? Import, blah, blah, blah. I'm pretty sure these are the tiny stories, but the examples are coming from, oh yeah, oh sorry, this is just a function in which you give examples as argument. It will contain these 3 columns, instruction, input, and output. And then you just load the data set and train. Now, guys, look at the trainer layer. The SFT trainer comes from TRL. TRL library should be your good friend for fine-tuning. It's a good fine-tuning model because it also supports reinforcement learning. Right? RL, in fact, in that stands for reinforcement learning. So, but you can do not just reinforcement learning, you can do this. So SFT, did we encounter the acronym SFT today morning? Supervised fine-tuning, exactly. So you just take a simple supervised fine-tuner from this library and just run at it. Very simple. You see trainer, and guess what the next line will be? Trainer.train somewhere. Oh, there we go, trainer.train, isn't it? Batch number this, batch size, total number of batches 8, number of trainable parameters 50,000. So now observe something, guys. Total number of trainable parameters is only 50 million. How is that possible when you took a 7 billion parameter model? What is 1% of 7 billion? Right? 70 million, right? Yeah, that is it. So it is the reason you get away with it is because of the LoRa. Because all the tunable parameters, the only thing you tune is the LoRa adapter. Right? And what is this LoRa business? I'll recap for you. So when you look at it, by the way, do you notice that the training loss, it starts at a 1.73, 2.3. It sort of goes up and down, but yeah, you can decrease it to some extent. It makes some progress. And then continue, then you ask it to continue the Fibonacci series and it will produce the output for you. Yeah. By the way, if your data set is huge, you can use the text streamer. Right. Now, this is an example. You can load the model, fine tune it, etc. I didn't find this example. And then those of you who are fond of, oh, by the way, once you have done that 4-bit, you want to save it back to, convert it back to 16-bit. Why? Because many of these LLM runners, they need the full model in 16-bit. Right? So you can upscale it back. GGUF, very popular with the llama.cpp. Right? You can do that.
So
now,
when you upscale, it's like padding with zeros?
Yeah, it's basically that. Converting the data. It's just as simple as converting the data type. Right?
So Asif, how do you know which LoRa to choose here? Or is it?
Oh, that is straightforward. That you'll learn in a moment. Let's get to LoRa's. But if you look at it,
can you just briefly talk about the data set, Asif, sir?
Yeah. So in fact, this data set is too trivial. Let me take a better example, which you'll like. This tiny, oh gosh. No, one second. Yeah. Support vectors. Yeah. So here is this data set. This tiny stories that I just talked about. Do you remember? Anybody remembers the tiny stories data set? Short stories. Yeah. So, right. So once upon a time, there was a little car named Beep. Beep loved to go fast and play in the sun, blah, blah, blah. Oh, I see. Right? This kind of stories. It's simple. So now, so think about it this way. Let's set the context. You have a LLM, think Llama or 7 billion parameter. It's a general purpose LLM, right? It can do many things. Now you want to fine tune it to do story writing better. So what do you need to do? You just need to fine tune it with lots of stories. Right? What does it mean? Give it next word prediction task, right? Simple causal model, treat it as a causal model, a language model, have a causal loss function, namely next word prediction. Is it producing the next words correctly? Right? In the story, you give a few lines and then say, okay, what is the next word, right? You can do it. And then at the end of that fine tuning, what should it be better at? Writing stories.
But we are not using instruction framework for
it. It is instruction framework.
The causal.
No. This in this simple situation, it is too simple a situation.
I see.
Yeah. You're just saying you have to continue the story. That's it. Yeah. So let's look at that. This part is just versioning and blah, blah, blah. Just make sure you install Unslot. That's the only extra dependency. From Unslot, the same fast language model. From pre-train, this looks very much like Transformer or PyTorch. So guys, if you know Hugging Faces and PyTorch well, right, everything pretty much conforms to a similar standard, right? So now let's look at that, LoRa. We now add LoRa adapters so that only 1 to 10% of the parameters will need tuning. So here it is. LoRa has certain parameters built in, tunable parameters. Dropout, 0, bias, none. These are all parameters. So by the way, these values are very generic. Most of the time you keep it like this. Right. Use gradient checkpointing, true, because it will checkpoint some of the gradients, random states. Yeah.
So you're converting into a LoRa.
No, LoRa is on the side, no? You keep the model there, you fine tune only the LoRa. Anyway, I'll review LoRa in a moment. Look at that. You train this LoRa, here's the data set, all these stories are there, training the model. Guys, do you notice that the training model is exactly the same? There's nothing different. Training loop is the same. Upper device training batch size 2, gradient accumulation step 4. By the way, if you base it on your hardware, what kind of hardware you're setting up on, right? If you're setting, for example, if you have Colab and you have A100, you can run the notebook as it, not only as it is, you can scale it up a little bit, right? Increase the batch sizes, you can play around with these things. A100, actually Colab is, frankly, for learning some of these techniques, Colab is really a very good friend, because for what is it, $10 or $50 a month, you get unlimited use, right? And imagine getting access to A100s.
For more than that, like if you have it connected to GCP, you can set up whatever backend you want to as well.
That is true. That's true, yes.
But $10 a month, is it?
It could be even less if you have it set up for GCP. Because then it's up for one.
So then we don't need so-called boxes.
And like the entire purpose of having it connected to GCP is so that they would just get everybody to use it securely.
Yes. See, this is their loss leader. They get you hooked onto Colab, and then after that,
No, first they get you hooked onto docs, and then Colab because
Yeah.
it's easy, and then you can
Right.
never leave.
never leave. Yes. So look at this run, and you see that the loss has gone down from not remarkably actually. It has gone down from 1.54 to, by the time you're done with the runs, to 1.24. May not look great, but actually it does seem to work. You should run it for far more epochs, by the way. 1 second, guys, I'll take questions. Now let's look at the inference. Once upon a time in a galaxy far, far away, suppose you give this as an input. So what will this machine do? It will continue, right? It will keep producing tokens. And let's see what it produces. You would realize that compared to the normal model, it does a much better job. You can try it out. Take Olama, just load this model and try to give this input and see what comes out. And you will notice that it produces a better result. Who is asking the question?
Yeah, so I understand the data set what here is more of a short stories, and you are just kind of training it on the same data set. But what if the instruction framework, if we have to use, where you have query and answer, question and answer part. So to generate that, you probably. So I'm thinking like.
No, look at the previous one. The last one is that. This example is that what is a famous tower in Paris? Input, output, right? So
then, my idea is like if we extend the RAG,
yeah,
after the RAG, the whole request to response is over. If I want to feed this as a fine tuning into my LLM,
yeah.
So how do I pair up? Do I have to
see? Here is the thing: RAG and fine tuning are orthogonal. RAG says leave the model as is. We can give it more facts to answer. So LoRa, what RAG gives you is more up-to-date information. What fine-tuning gives you is it changes the behavior of the LLM.
And what I'm saying is in the end, I want to put this information back to LLM, so that LLM is more aware of going forward and make use of fine-tuned LLM.
That is fine-tuned LLM. So what people do, see, the gold standard is do RAG on a fine-tuned LLM. That is the gold standard.
But if I'm doing a RAG and teaching RAG, whatever the RAG's output is, into LLM, so I'm trying to invent a method to fine-tune LLM on my data.
See, remember we talked about this, Prakash. Anytime you fine tune LLM, it is not a complete blessing because now your LLM knows that data and somebody can steal the data from the LLM. So there are high sensitive, very sensitive or confidential data. Our model should never be fine tuned.
But this model is living on the internal.
No problem. It is living internally. But once people come to know that you have a model which can leak out confidential data if you try, they will find a way to get to that model. Yeah. See, think about it this way. Confidential data is most secure when it is in a vault, never in the memory of a computer. Right? And whatever the model learns becomes its parametric memory.
And I'm trying to say, let's say these are the data is already known to internal engineering. I'm trying to implement something. I can take it offline also.
Yeah. Let's discuss your specific use case and I'll give you advice accordingly. Right. So guys, that is Onslaught. I want you guys to run this today. So today what I'll do is we have limited time. It's 3 o'clock. Let me run through what I want you guys to do. So can you guys please run this notebook, storytelling notebook, text completion storytelling. In the same way, there is another paper, which is Llama Factory, that has recently gained quite a bit of attention. What Llama Factory does, it says unified efficient fine-tuning of 100 plus language models. Another framework in which you can do fine-tuning. So this is the GitHub site for Llama Factory. And by the way, these are all, look at this. This project sort of recent, it's fairly recent. And see how many stars it has already. 14,000 stars. So I'm not showing you some minor projects. These are heavyweight projects out there. Right? So Llama Factory is also getting a lot of attention and attraction. Their main mantra is easy and efficient LLM fine-tuning. Right? The question that frankly comes to my mind is, how much easier do you want to make it? Right?
So this is coming from Meta or somebody outside?
No, this is coming from a group called, hang on, I'll remember. I forgot actually who is doing this. So anyway, this is that and it does very well. Right? So Llama Factory is something. Now, what do I want you to do, Llama Factory guys? I've just given you one notebook each. Just run this notebook. Yeah. On that. This is the storytelling notebook. Anyway, I won't go into that. Try it out. Just do the same storytelling on Llama Factory. Guys, are we getting the assignment? Do the storytelling fine-tuning with Onslaught and with Llama Factory.
Yes.
Next, we come to the big topic, very, very big topic of today, which is parameter efficient fine-tuning. So for that, Peft, let's take a 10-minute break and then I'll start with this. All right, guys?